Hi guys! Now that you know how to create mathematical models of engineering systems, now that you know how to use Laplace transform to solve the linear differential equations of these systems, we are now going to look into transfer functions, how we use them and what they are exactly. Transfer functions represent the input-output relationship of systems. They allow to simplify complicated systems using block diagrams. So what this means is that a transfer function is a function in which you input a signal, a value, a variable, and then you get an output from that very input. We can represent it using block diagrams. Block diagrams are just blocks which represent the function and are very easy to visualize, exactly like shown on this slide right here. So you have the input going into the block representing the transfer function, here called GS, and then the transfer function outputs a signal going out of the block. So to sum up, a transfer function is the algebraic relationship between the input signal and the output signal of a linear system. For a system with input signal ut and output signal xt, we can write the following block diagram. We use Laplace transform because they make it so much easier to calculate everything. Okay, so if you look at that block diagram, you have us going into the transfer function gs. Okay, this means that the two are multiplied together. The fact that gs output xs means that gs multiplied by us, the two multiplied together, actually became xs. This is how you have to see a block diagram. Okay, so you can write that xs is equal to gs us, which gives the transfer function gs is equal to xs divided by us. So it's quite simple. You have an initial signal us which goes through gs, so you can multiply the two together. That's what it means when I say it goes through. And gs multiplied by us becomes xs. So mathematically it's xs equals gs multiplied by us, and then you can isolate the transfer function as gs equals xs over us. It's always easier to understand these kind of concepts through examples. So let's look again at our example of the 1 degree of freedom oscillator. We have the equation that we calculated in one of our first lectures, that the mass m multiplied by the acceleration of that mass plus the damping coefficient of the damper multiplied by the velocity of the mass plus the spring constant of the spring, obviously, multiplied by the displacement of the mass is equal to the force applied on the mass. So as a little reminder, the first term is due to the second law of Newton, the second term is the equation for a damper, the third term is the equation for a spring, and the force, is the input that is exciting the whole system. So here, the initial conditions are that the mass has zero velocity at time equals 0, and it has zero position at time equals 0. So it hasn't moved and it has zero velocity when the whole system starts, okay, when time actually activates in this system. Okay, so the initial conditions are actually 0. The input in the system in that case is the force F with respect to time. So we can apply Laplace transform onto this and we get Fs. The output of this system is the position of the mass m. So x with respect to time, and applying a Laplace transform onto this, it becomes Sxs. So we can take the Laplace transform of the differential equation that represents this engineering system. Okay, applying that Laplace transform with the linearity property and using the derivation rule from the table, we get that the equation comes back to the mass m multiplied by s squared times xs plus the damping coefficient c times s times xs plus k, the spring constant, multiplied by xs equals the Laplace transform of the force Fs. you can notice that because our initial conditions are 0, we don't have any extra term that come with the Laplace transform of derivatives. Okay, it's the easiest case. So now simply we can factor everything by excess. So you regroup all the terms that are multiplied by excess, and you can then divide them on the left and on the right, and you get that excess is equal to the Laplace transform of the force, Fs, divided by ms squared plus cs plus k. So again, it's quite a simple expression that we got from an initially complicated one due to the derivatives and thanks to the Laplace transform. So if you look carefully at what we have now, we have excess equals an expression, which here is 1 over ms squared plus cs plus k, multiplied by fs. If you remember, fs is the input, excess is the output. Fs is what we know is happening to the system, and excess is what we want to find out happens after the force has been applied. Okay, so if you look at it, you can see that that term in the middle is actually the transfer function gs. It is multiplied by the input to give the output. So you can then write that xs equal gs, which is the plant transfer function, the system's transfer function, and that is multiplied to the input fs. And you can write this in the form of a block diagram, as you can see here. So fs goes in the block of gs, and the output is xs. We are now going to define some parameters that you can easily find from a transfer function that usually characterize the behavior of the system that is represented by the transfer function. Okay, so these parameters are called poles and zeros. So first, to understand them, you can see from our previous example that the transfer function is always made of a numerator, which is the term on top of the fraction, and the denominator, which is the term below the fraction. Okay, the order of the numerator, which is what is its power essentially, is called m. The order of the denominator is called n in this case. Okay, and in general, you will always get that the order of the numerator is superior or equal to the order of the numerator. Okay, if you are one day asked for the relative degree of a transfer function, it is the denominator minus the numerator. It has to be positive. So what is a zero? It's easy to remember because a zero is essentially when the transfer function is equal to 0. So it has to be that the numerator is equal to 0. So zeros are all the points at which the numerator is equal to 0. Okay, so it's any value of s that makes n of s equal 0. A pole, on the other hand, is essentially any value at which the transfer function becomes infinite. It's indeterminate, it has no value. And this happens in a fraction when the denominator is equal to 0. So the poles are any value of s that make ds, the denominator, equal to 0. This is actually where the fact that s is a complex number comes into play. Let's look at this through an example. We have the transfer function gs equals s plus 2 over s squared plus 4s plus 3. As you can see, everything is in order because the order of the denominator is higher than the order of the numerator. Okay, the denominator is of second order, whereas the numerator is of first order. You can then factor this expression very easily to find that the zero of the transfer function is actually s plus 2 equals 0, and the poles of the transfer function occur when s plus 1 is equal to 0 or s plus 3 is equal to 0. So you get that the 0 is at minus 2, while one of the poles is at minus 1 and the other pole is at minus 3. In this case, it's quite easy because the solution of s is a real number. There is no complex part to that solution. Okay, we can then plot this on the s-plane. The s-plane is essentially the complex plane. You have the vertical axis that represents the imaginary number, and the horizontal axis that represents the real number. Okay, so we can place our 0 as a circle and our poles as crosses. So I just want to give a little comment about zeros and poles. Usually when a transfer function has a 0, it means that the response will have an overshoot. We'll see exactly what this means later. The poles actually help us find out before computing anything if this transfer function is going to lead to a stable system or an unstable system. If the poles are negative, then it's all good. The system is going to be stable. Actually, the more negative they are, the more stable the system is. However, if the poles are actually positive, then the system becomes unstable. This is it about transfer functions, poles, and zeros. As usual, if you have any questions, please do not hesitate to ask me. I'll be very happy to help you. Thank you very much, guys.